The outer solar system is tilted, not metaphorically, physically. The plane where the planets orbit the sun is off by 15 degrees from where the physics says it should be. 15 degrees doesn't sound like much until you understand what that number is measuring. The collective gravitational signature of everything in the outer solar system added up over billions of years. That signature is wrong, and nothing we know about puts it there. Here's what the solar system is supposed to look like. The 8 known planets orbit roughly in a flat disk, the ecliptic plane, a remnant of the spinning cloud of gas and dust the sun condensed from 4.5 billion years ago. That disk isn't perfectly flat, but the deviations are small and accountable. We know what's out there. We've mapped it. The math closes, except it doesn't. When astronomers look at the orbital plane of the outer solar system, the trans-Neptunian region, the distant belt of icy bodies beyond Neptune's orbit, the plane is warped, tilted by 15 degrees relative to the invariable plane, which is the truest flat reference we have. Calculated from the angular momentum of the entire solar system, something massive has pulled that region out of alignment, or is still pulling it. The warp itself isn't new. It's been sitting in the data for years, noted, filed, not fully explained. What's new is that a team at Princeton decided to take it seriously as a gravitational signal rather than noise, and asked the obvious question nobody had pushed all the way to an answer. What exactly would have to exist out there to produce this specific tilt, at this specific magnitude, in this specific direction? That's a harder question than it sounds, because the warp isn't a single object's fingerprint. It's the integrated effect of something on an enormous population of smaller bodies over geological timescales. To reverse engineer it, you need to account for the known planets, the known Kuiper belt structure, the known distribution of trans-Neptunian objects. Subtract all of that out, and see what gravitational residue is left over. What's still pulling when everything accounted for has been accounted for. What they found when they did that is the subject of the rest of this video. But before we get to the answer, stay with the anomaly for a moment, because it matters that you feel the weight of it. 15 degrees. In a system that has been gravitationally settling for 4.5 billion years. In a region we have been surveying seriously for decades, the warp is real, it's large, and every model of the outer solar system that doesn't include something new to explain it is, by definition, incomplete. The question isn't whether something is out there, the question is what. So that's what the Princeton team set out to quantify. Not just to confirm the warp exists, but to ask what precisely would have to exist to produce it. The process is called gravitational inversion. You start with an observed effect, the tilted orbital plane, the statistical clustering, the 15-degree signature baked into the trajectories of hundreds of trans-Neptunian objects, and you work backwards. You treat the distortion as a constraint. Every property of the unknown mass has to be consistent with every aspect of what you see. Too light and the perturbation is too weak to produce this warp. Too heavy and the signature is too strong, or it would have already pulled something else visibly off course. Too far and the gravitational influence is too diluted over too wide an area. Too close and we'd have found it already. What you're left with, when you've tightened all those constraints simultaneously, is a window, a range of masses and orbital distances where a single solution survives. And what the Princeton analysis found is that the window is narrow. Mass, somewhere between 1 and a few times the mass of Mercury on the low end, up to Earth's mass on the high end. Not a gas giant, not a super-Earth, a rocky terrestrial-class body, the same category of planet as the 4 inner planets of our own solar system. Distance, between 80 and 200 astronomical units. 1 astronomical unit is the Earth-to-Sun distance, roughly 150 million kilometers. So we're talking about an object sitting somewhere between 8 and 20 times farther from the Sun than Neptune. Far, certainly, but not the deep outer solar system abyss that most people picture when they hear about undiscovered planets. Neptune is at 30 AU. This thing, if it's real, is at a distance that puts it inside what planetary scientists still consider the accessible outer solar system. That last part is the detail that stopped people when the paper circulated. Because the instinct, when you hear about a missing planet inferred from gravitational anomalies, is to picture something impossibly remote, a dim body thousands of AU out, practically in interstellar space. That's the mental model Planet 9 built, but the Princeton numbers don't point there. They point much closer. Close enough that the absence of a confirmed detection starts to feel like a puzzle rather than an excuse. The team ran the orbital mechanics forward and backward, They checked whether an object in this mass and distance range could produce the warp without creating other distortions we have already noticed. Perturbations to Neptune's orbit, anomalies in Kuiper belt structure that surveys have explicitly ruled out. It fits, not as one possibility among many, as the solution that doesn't break anything else we know. They called it Planet Y, not as a definitive name, as a placeholder for something the math demands and observation hasn't yet confirmed. A variable in an equation that currently has only one solution. The question that follows immediately, is this the same thing people have been calling Planet 9 for the last decade? The answer is no, and the distinction matters more than it might seem. Planet 9 has been a fixture of solar system speculation since 2016, when Caltech astronomers Konstantin Batygin and Mike Brown proposed it to explain a different anomaly, the clustering of distant Kuiper belt objects, whose orbits seem to be herded into alignment by something massive pulling from far out in the dark. That something, they argued, was a planet roughly 10 times Earth's mass, orbiting somewhere between 400 and 800 astronomical units from the Sun, nearly a light week away. Cold, slow, and enormous. Planet Y is not that, not even close. The differences aren't subtle. They run through every dimension that matters. How big it is, how far it is, and what it's actually doing to the solar system. Start with mass. Planet 9, if it exists, is a super-Earth at minimum. Some estimates push it toward a small Neptune, a world with a thick atmosphere and a gravity well deep enough to shepherd entire populations of Kuiper belt objects across decades-long orbits. Planet Y is rocky, Mercury-to-Earth-mass. The Princeton team isn't describing a gas giant lurking at the edge of detection. They're describing something geologically more like the inner planets. Dense, comparatively small. A world you'd recognize in structure, if not in context. Then there's the distance. 400 to 800 astronomical units for Planet 9. 80 to 200 for Planet Y. That gap is not a rounding error. At 80 astronomical units, Planet Y is twice as far from the Sun as Pluto. But at 400, Planet 9 is 5 times further than that, orbiting in a regime so remote that its year, if it exists, spans 10 to 20,000 of ours. Planet Y, by comparison, is almost embarrassingly nearby. It's the kind of distance that makes you wonder how we missed it, which is exactly the question the next act will answer. And the mechanism is different. Planet 9 was proposed to explain orbital clustering, the gravitational herding of small, scattered objects. Planet Y was derived from a warp in the orbital plane of the outer solar system itself. These are distinct physical signatures. A body producing one wouldn't necessarily produce the other. The two hypotheses aren't competing explanations for the same data. They're responses to different problems, pointing at different places, with different physical properties. Conflating them doesn't sharpen the picture. It blurs two separate questions into one muddy non-answer. Neither has been confirmed. Both remain mathematical inferences, a demanded solution, not yet a found one. But they are not the same inference, and treating them as interchangeable has already caused confusion about what the Princeton result actually claims. Planet Y doesn't vindicate or undermine Planet 9. It stands alone, and it raises a question Planet 9 never had to answer. Where did it come from? Where it came from is not a secondary question. It's the one that makes this discovery genuinely strange, because there are two answers, and they cannot both be true. And they would each mean something completely different about the solar system we thought we understood. The first possibility, Planet Y formed here. It grew in the same disk of gas and dust as everything else, the same raw material that made Mercury, Venus, Earth the gas giants. In the early solar system, planetary formation was chaotic. Objects were flung outward on elongated orbits by gravitational interactions with Jupiter and Saturn. Most of those objects were ejected entirely, launched into interstellar space, lost forever. But some weren't. Some settled into distant, stable orbits and stayed. On this scenario, Planet Y is a survivor. A native body that got kicked far out and never came back, quietly orbiting at 80, 100, maybe 200 AU for 4.5 billion years, waiting to be noticed. That would already complicate the standard model. Current formation theory doesn't predict a rocky body of that mass surviving at that distance. Its presence would force a revision of how we think planetary material was distributed in the early solar system, how far out solid bodies could grow, how the giant planets reshaped everything beyond them. Uncomfortable, but manageable. The solar system gets a little messier. The models get refined. Science moves on. The second possibility, is not manageable in the same way. The second possibility is that planet Y did not form here at all, that it formed around another star entirely, was ejected from that system when its own giants reshuffled their orbits, and then wandered interstellar space as a rogue planet until the sun's gravity caught it, captured it, absorbed it into our solar system billions of years ago, and it has been circling here ever since, on a tilted, inclined orbit that doesn't quite match anything native, because it isn't. That scenario lands differently, not just because it's stranger, because of what it implies at scale. Rogue planets aren't rare. Current estimates suggest there may be more free-floating planets in the galaxy than there are stars. They're produced constantly, whenever a young planetary system goes dynamically unstable and hurls its members outward. If one of those wanderers could end up captured by our sun, then capture events aren't exotic accidents. They're something that happens, maybe routinely, to stars with wide gravitationally active outer regions. Every star in the galaxy may have done this. The outer solar system, on this picture, isn't just the solar system we were born with, it's a collection site. A place where our sun, over billions of years, may have swept up objects that began their lives somewhere else entirely, around stars we'll never identify, in planetary systems that no longer exist in their original form. Distinguishing between these two scenarios from the orbital data alone is hard. A native body on a scattered orbit and a captured rogue on a bound orbit can look similar from the outside. What separates them is the fine structure, the exact shape of the orbit, the inclination relative to the solar plane, the eccentricity. Those details are precisely what you can't extract until you've actually found the object and tracked it, which means the origin question stays open until detection does. But it is not an idle question. It is the difference between a solar system that is slightly messier than we thought, and one that has been quietly trading members with the rest of the galaxy for 4 billion years. So the origin question stays open, and it stays open for a specific, frustrating reason. We haven't found the object. Not because nobody's looked, because looking at this distance is nearly impossible with the instruments we've had until now. Here's the core problem. Every telescope we've ever pointed at the outer solar system relies on reflected sunlight. A planet shines because the sun hits it, and some fraction of that light bounces back toward us. That fraction follows an inverse square law. Twice the distance, 1/4 the brightness. Except the light has to make the trip twice, out from the sun to the object, then back from the object to us. So it's not inverse square, it's inverse to the 4th power of the distance. At 1 AU, Earth's distance from the sun, a rocky body reflects a certain amount of light. Move that same body to 100 AU and the reflected light reaching us doesn't drop by a factor of 100, it drops by a factor of 100 million. The object we're looking for, sitting somewhere between 80 and 200 AU, would be roughly 14 billion times fainter than it would appear from where we're standing. That number is not a typo. For context, the faintest objects the Hubble Space Telescope can image are about 31 on the astronomical magnitude scale. A Mercury-to-Earth-mass body at 100 AU sits right at the edge of that, possibly beyond it, depending on its surface reflectivity. And Hubble isn't surveying the whole sky, it's a pointed instrument. You have to already know roughly where to look. Wide-field surveys have run. The Wide-Field Infrared Survey Explorer, WISE, scanned the entire sky in infrared. It would have caught a large warm body, something Jupiter mass or bigger, out to several hundred AU. Planet Y is not that. It's a cold, rocky object, smaller by an order of magnitude, barely warmer than the space around it. WISE wasn't sensitive enough. Neither was Pan-STARRS at the relevant distances, nor the older SDSS catalogs. The orbital arc is the other problem. To confirm a distant object as a planet rather than a noise spike, you need to watch it move across multiple observations, years apart, ideally, to calculate a proper orbit. At 80 to 200 AUW, Planet Y is moving slowly. Decades of tracking time, potentially. You need to find it first. And finding it requires surveying enormous swaths of sky, repeatedly, at a depth no telescope has managed at scale. Until now. That instrument is the Vera C. Rubin Observatory, and it was built almost as if on purpose for exactly this problem. It sits on Cerro Pachon in the Chilean Andes at roughly 2,600 meters elevation, above most of the atmosphere's water vapor, above the light pollution of the valleys below, pointed at the southern sky. The telescope itself has an 8-meter primary mirror, which is large but not uniquely so. What makes Rubin unlike anything before it is the camera attached to that mirror. The LSST camera, Legacy Survey of Space and Time camera, is the largest digital camera ever built for astronomy. 3,200 megapixels, a single image covers an area of sky about 49 square degrees, which means it captures roughly 40 full moons in one exposure. That single-frame footprint is what changes the math. Every telescope before Rubin faced the same impossible trade-off: go deep enough to see faint, distant objects, and your field of view narrows to a postage stamp. Widen your field to survey large swaths of sky, and you lose the depth to see something cold and rocky at 100 AU. Rubin breaks that trade-off. It is deep and wide at the same time, sensitive enough to catch objects roughly 100 times fainter than pan-stars could manage at the distances we care about, and broad enough to map the entire southern sky in a single night's observing. Not in a week, not across a season. Every 3 nights, the entire southern sky, cataloged, stacked, compared against the last pass. Over 10 years, the Legacy Survey of Space and Time will image the same patches of sky roughly 800 times each. That repeat cadence is the key. A noise spike stays a noise spike. A planet moves. Slowly, yes, but across hundreds of observations, an object at 80 to 200 ADU will accumulate enough positional shift to distinguish it from background stars, from artifacts, from the long list of things that fool a single survey. The survey began full science operations in 2025. The data pipeline behind it is designed to flag moving objects in near real time, alerts going out within 60 seconds of an image being processed. Thousands of new solar system objects will be cataloged in the first year alone. Most will be mundane. Kuiper Belt objects, distant asteroids, known bodies revisited at higher precision. But somewhere in that catalog, if Planet Y exists at the location the Princeton math points to, it will appear. Not as a dramatic discovery moment, more likely as a faint dot that moves wrong, flagged by the pipeline, passed to follow-up observers, and then tracked for months until the orbit hardens into something undeniable. That is what confirmation looks like in practice. Not a press conference with a single image, a slow accumulation of positions, a trajectory taking shape, a mass estimate converging. Rubin gives us, for the first time, the depth and the cadence to run that process at the scale the outer solar system demands. The detection gap that has sheltered Planet Y since the solar system formed is finally closing. So say the dot appears, say the orbit hardens, say the mass estimate converges on something between Mercury and Earth, sitting at 140 astronomical units, exactly where the Princeton math points. What breaks? Start with solar system formation, because that is where the fractures run deepest. The standard model, the one built over decades to explain the 8 planets, the Kuiper Belt, the scattered disk, does not produce a terrestrial body at 80 to 200 AU. The physics of planetary accretion at that distance doesn't work. The disk was too thin, the orbital timescales too long, the material too sparse. You cannot grow a rocky planet that far out from scratch. Which means if Planet Y is there and it is rocky, the model is wrong in one of 2 ways. Either it formed somewhere else and migrated outward, an event our models allow but have never required, or it was never ours to begin with. That second option is the one that pulls everything loose. Because if the sun captured a planet from another star system, a rogue, wandering through the early galaxy when stellar nurseries were dense and close encounters were common, then the solar system's history is not the closed story we have been telling. It has an outside chapter, a planet that formed under a different star, in a different disk, with a different chemistry, and then was stolen by our sun's gravity and locked into a wide, tilted orbit it has kept for billions of years. Here is where the implication stops being about our solar system and starts being about every solar system. The conditions that would have allowed the sun to capture a rogue planet, a young, dense stellar cluster, a slow enough encounter, a gravitational assist at the right geometry. Those conditions were not unique to us. They were the default environment of early star formation across the galaxy. If it happened here, the math says it almost certainly happened elsewhere. Many elsewheres. What we have called rogue planets, the free-floating objects drifting between stars, estimated to outnumber stars in some models, may not be wanderers so much as traded cargo. Captured, lost, recaptured, circulating between systems across billions of years. And then there is what confirmation does to exoplanet science. Every architecture we have inferred for distant solar systems, every population of planets we have cataloged, every gap we have explained, every anomaly we have written off, was built on the assumption that planets stay where they form. Planet Y, if confirmed, removes that assumption. The outer edges of planetary systems become dynamic in a way the models have not fully accounted for. The population of wide-orbit planets around other stars may be larger and stranger than the surveys suggest. None of this is certain yet. The cascade of implications only triggers if the dot appears, if the orbit resolves, if the mass estimate holds. But science moves in exactly this direction. A single confirmed anomaly, in the right place, can rewrite the context for everything else. Planet Y would be that anomaly. Not just a new planet, a key that unlocks a different version of where we came from. That key exists now. The math produced it. The question is whether the lock is real. Here is where the story stops being history and becomes something rarer, a prediction with a deadline. The Vera C. Rubin Observatory is operational. Its legacy survey of space and time has begun, and the timeline it sets for this particular question is not vague. It is not sometime this century or when technology allows. It is roughly 10 years. A decade from now, the outer solar system will have been mapped with a depth and cadence that no prior instrument could match, and planet Y will either be in that map or it won't. That specificity is almost strange when you sit with it. For most of human history, questions about what orbits the sun were answered on geological timescales. Uranus discovered by accident in 1781. Neptune inferred from math and confirmed 7 months later in 1846. Pluto found after a systematic search that took years and still nearly missed it. Each discovery required a particular instrument, a particular moment, a particular piece of luck. Planet Y requires none of that luck. The instrument exists. The search strategy is defined. The only variable left is whether the object is there. If it is, the discovery will not look dramatic at first. A faint point of light, slightly shifting position between one Rubin frame and the next, flagged by software that processes 10 million alerts a night. It will be confirmed by follow-up observations over weeks or months, an orbit slowly resolving from a smear into a path, a mass estimate tightening from a range into a number. The announcement, when it comes, will be careful and hedged and full of error bars, and then the implications, everything laid out in the acts before this one, will begin to propagate. If it isn't there, if Rubin maps the entire candidate region and finds nothing, that result matters too. It means the 15-degree warp has a different explanation, or no explanation that current physics can supply. It means the Princeton team's model, elegant as it is, was solving for something that doesn't exist. Null results in science are not failures. They are boundaries. They tell you where reality stops tolerating a particular idea. Either way, within a decade we will know. That is the clean fact sitting at the end of this story. Not we might know, or we could know if funding holds and instruments cooperate. We will know. The math is pointed. The telescope is running. For the first time since anyone has been asking whether the solar system has more planets than the 8 we teach in classrooms. The answer is close enough to have a deadline. 10 years on the clock. The outer solar system is about to stop keeping its secrets.